Alright guys, so before we start looking at how perpendicular bisectors and angle bisectors affect triangles, let's have a little quick review on the Pythagorean Theorem. If I wasn't smart enough to give you a quick review on it before, let me give it to you now. Here we have a right triangle. And in a right triangle, if we know two legs of the triangle, let's say that this is A and that this is B, well then we can find C, the hypotenuse of the triangle. This formula works for the hypotenuse, and if you don't know what the hypotenuse is, just remember that the hypotenuse is the side of the triangle directly across from the 90 degrees. And the Pythagorean theorem, I'm sure you've seen it before, looks like this. And what that says is that if I know these two legs, I can find the hypotenuse. So let's say this is 3, and let's say this is 4. Let's see if we can find the hypotenuse now. I don't want C squared. I want regular C. So I have to take the square root of both sides. The square root of C squared is C. The square root of 25 is 5. And C is equal to 5. This is a nifty trick to know when we're doing complicated triangles. Take a look at number 13. Number 13, they tell us that the perpendicular bisectors of this triangle meet at point G. I'm sorry. Let's try that again. The perpendicular bisectors of a triangle are these right here. I know that they're perpendicular because I can see the right angles to the sides. I can see that segment GE is perpendicular to segment AC. I can see that segment GF is perpendicular to segment BC. And I can see that segment GD is perpendicular to segment AB. I also know that it's bisecting it because I have these congruency dashes here. I can see that segment AC is broken up into these two equal segments. I can see that segment BC is broken up into these two equal segments. And I can see that segment AB is broken up into these two congruent segments. Now, this dot right here, where all the perpendicular bisectors meet, is called the circumcenter. And I know that the circumcenter is the same distance from all of the vertices. The circumcenter, which is made by perpendicular bisectors, is the same distance from all the vertices. So I know that this segment, and this segment are all the same. So if this is 7, this is 7, and this is also 7, which means that G to C is 7 units long. Question number 3 is a little bit different because now I don't have perpendicular bisectors. I have angle bisectors meeting at a point. So here's one angle bisector, here's another angle bisector, and there's another angle bisector. And the point where they all meet is called the incenter of a triangle. And I know that the incenter is equidistant or the same distance from all the sides of the triangle. So I know that this segment, and this segment are all the same size. Now, that's pretty interesting. I have a point, and I have 1, 2, and 3 segments that are all the same distance from that center point. That should remind you of a particular polygon we talked about before, and that is a circle. If you remember, a circle has a center, and all the rays are the same distance from that center. So if MJ is 5, then MK is 5, and ML is 5. So then MK, we know, is 5. Now let's take a second to do questions 14 through 17. On question number 14, again, they tell me that I'm dealing with perpendicular bisectors. Perpendicular bisectors. So here's a perpendicular, there's a perpendicular, there's a perpendicular, and they tell me that they're perpendicular bisectors. You're going to notice that this time they didn't mark any of the sides. They didn't give any dashes here like this, or like that. They didn't do any of that. One, because we don't need it for this question, and two, because they might be trying to trick you. But they're telling you that these are perpendicular bisectors, so you can assume, because they're telling you that these sides are both equal, that both of these segments are equal, and that both of these sides are equal as well. But now I have perpendicular bisectors coming together at point D. Well, I should know by now that this point is called a circumcenter. And I know that the circumcenter is the same distance from all of the vertices. So I know that this is the same length as this and that. So if ds is 9, then I know that dt is also 9, and I know that dr is also 9. So the distance to dr is 9. Next, now I have angle bisectors. Now I have angle bisectors. Well, here's one angle bisector, here's another angle bisector, and here's another angle bisector. And all my angle bisectors are meeting at point W, which by now I hope you know is called an incenter. Okay? And I know that the incenter is the same distance from all of the sides. From all of the sides. And you might be saying to yourself, Mr. C, but those don't look the same. It kind of looks to me like, it kind of looks to me like these two here are shorter than this one here. And that's okay that it looks that way. But let's take a look at another triangle. Let's take a look at this triangle here. Let's pretend for a second that we're looking at all of these perpendicular lines here to the sides. I think we can agree that they're pretty much similar in size. They almost look like they're all the same. But what if I take my triangle and now I just tilt it like this? Say I just tilt it like this. Well, now what happens to this line right here is that it gets shorter and shorter while these lines still look long. They look the same this way, but if I tilt it, look how short this line gets. It gets pretty short while these still look pretty long. And that's what could be happening here. So even they might look like they're shorter. In actuality, it might be a triangle that's just been tilted. But you know what? That doesn't even matter, because what matters is that I know that these are angle bisectors. And if these are angle bisectors, I know this is an incenter, and then I know that these have to be the same size. So if WC is 20, then WB is also 20, and WA is also 20. So WB is 20. Next, again, I'm dealing with angle bisectors. So here's one angle bisector, there's another angle bisector, there's another angle bisector. Well, if these are angle bisectors, then I know that if these are angle bisectors, then I know that this is a incenter. And then that means that I know that these sides are the same distance from all the sides of the triangle. Now, are these perpendicular bisectors? I don't know. I don't have any proof that tells me that they're perpendicular bisectors. What I do know is that all of these are going to be the same size. Now, if you notice here, they told me that this is 5. Now, this incenter right here is the same distance, this incenter here is the same distance from J as it is this incenter is the same distance from B as it is to C as it is to A. So I know that these here are the same. But I also know that if this point is this far away from J and this is 4, then I know that since this point is the same distance, I'm going to know that this is also 4. And now I can find b. And how am I going to find b? I'm going to find it using the Pythagorean theorem. Because if this is 90 degrees here, then I know that this is also 90 degrees here. And what I have is the hypotenuse and the leg of a right triangle. So I can use the Pythagorean theorem. Just remember that the hypotenuse is always which letter? Is it A, is it B, or is it C? If you guess C, you guess correctly. There's my Pythagorean theorem, where the hypotenuse is always C. Remember, I don't want b squared, I want just regular b. So I'm going to take the square root, and b is going to be equal to 3. So the distance from k to b is going to be 3. And let's take a look at the last question here. Now I'm dealing again with perpendicular bisectors. So I know that this is a perpendicular bisector, this is a perpendicular bisector, and this is a perpendicular bisector. So what I have here now, do I have an incenter or do I have a circumcenter? If you guess circumcenter, you guess correctly. Now in a circumcenter, I know that these diagonals are all from that this point is the same distance from all of the vertices. Okay? And I know that this is 7. I know that this is 48, and I know that this is a perpendicular bisector, so this is 24, and this is 24. Well, if this is 7 and this is 24, then I can find this missing side right here, this hypotenuse of the right triangle. And you might be saying, well, why is that useful? Why do I need to know what that side is? Well, remember that all of these, that this point is the same distance from all of the vertices. So if I find the length of this yellow line here, I'm also going to find the length of this yellow line here, because they're the same. And I am looking for q to n, and that is q to n. So I can find this side here using the Pythagorean theorem, where this is one leg, this is another leg, and this right here is the hypotenuse. So let's do the Pythagorean theorem. Remember, I don't want c squared, I just want c. So c, my hypotenuse is 25, which means then that this